that I've been working for a while to make sure that our customers and people in the open source community have access to tools to make working in deep learning, specifically with PyTorch, faster using Dask and GPU clusters. And so that's one of the topics that's interesting to me. And so I am going to be talking about that with you all today. And so I hope that you also find it valuable and interesting for your particular needs. Before we get too deep into that, though, I'm going to talk to you a little bit about Saturn Cloud and what we do. And before we even go that far, let me let my colleague Aaron introduce himself real briefly, and he's going to be your question and answer person throughout today's session.
Hi, everybody. Yep, so I'm just going to kind of be here more of a supporting front. If anybody has any questions, I'll be monitoring the chat, can help you out. Go ahead and join that Slack community if you want some kind of to continue conversations even beyond this Zoom, but I'm mostly just here to help. So reach out to me and send me a message if you need anything.
Awesome. And so for everyone's reference, we'll be doing a talking bit for a while here. I'm going to tell you about Saturn and about what we do and how our tools can be useful to you and make you more productive in your machine learning and data science use cases. And then I'm going to go through the demo of exactly how we have taken a single transfer learning task, so taking a pre-trained model and adapting it to a specific targeted use case. Using GPU clusters, and then I'm going to make sure that that we all have time for Q&A at the end. Make sure that there's plenty of opportunity for everyone to ask your questions and to get discussion going, and then we can carry that discussion on to our Slack and elsewhere. So, with no further ado, let me get us moving here. So, the thing that I think I would love to talk a little bit about first is sort of the workflow and opportunities that are maybe missed by data scientists because of the pain points that exist in our day-to-day work. Aaron and I have certainly got lots of experience in this area and seeing the struggles that we go through to just do the regular day-to-day work of data science in order to generate business valuable results. So we might encounter situations where out of memory errors, Aaron did a workshop on this in December that was incredibly insightful, because we run into situations where we have more data than we can actually ingest or house in memory, and therefore we're not able to do the kinds of modeling that we want to do, or we're not able to do them at the scale that we would find most valuable. There's also the situations where computation is slow. We've all been there, where there's that one model that you can't fail fast at because it takes so long to get to the point where it's either going to succeed and produce results that you need, or it's going to fail and tons of time will be wasted. You're going to get up and you're going to go get the coffee and you're going to wait for your model to be done. And so that's another pain point that we run into ourselves. There's also the challenges when you finally have a model that's going to work for your use case. You've developed it in sort of an R&D capacity, but deploying that to production, so really getting from a model that works to a model that's going to be customer value, business value generating, is like climbing Mount Everest in a swimsuit. It's the worst possible struggle to get from R&D to reality. And that's a big problem that we find lots of data scientists encounter. So then we get to, well, what if all of this is working well, but the tools are unreliable, but you can't get access to the tools that you need when you need them? If, say, things like installation failure, managing packages, environments are always coming up and going down. These are sorts of problems that Saturn Cloud is here to help all of this be preventable and avoidable for data science practitioners. We do, however, want to avoid certain things for the data scientist. DevOps is not the data scientist's job, and it shouldn't be the data scientist's job. For businesses, DevOps can be a huge cost center. It can be incredibly difficult to get the talent and to build up the skills internally to manage the DevOps needs. And Saturn Cloud can handle all of the DevOps for data science practitioners ourselves and leave you free to do other things. There's also an element of getting code from R&D to production in addition to the deployment process being really arduous, it can also be a problem of speed and being able to get the performance out of your code that you want to, especially if you're writing in Python. And what that can cause is the impetus to, well, you got to restructure it all. You got to rebuild it from scratch. You got to cut this out, move this over here, and then the R&D work that you did to start with is either no longer valuable and you're wasting a ton of extra time, or the end result may not even be possible to do in both production speed and in the way that you've written it in the first place. This could result in you getting stuck with, oh, well, why not go with Spark? Why not go with C++, Java, God forbid? And you're giving data scientists a whole extra layer of work that's not adding any new value. It's just taking work that's already been done and rewriting it again. Saturn Cloud wants to help customers avoid having to do any of this nonsense. And so that's one of the reasons that we have an ecosystem that I'll go through a little bit for you in a minute here to just describe exactly what's going on in the product and how this product can save you from all of these pain points that we've just talked about. So first, everything that you work on in Saturn Cloud can run in Python. We have parallelized clusters. We have a ton of resource availability for you, but you don't need to use anything except Python to do it. No C++, no Java, no Spark. The infrastructure that we make available to customers is Jupyter Labs in the cloud, full featured. It's not a pared down sort of cut and pasty version of it. It's the full tool. And so this means that we have a full platform of data science toolkits that is all Python based. And the place where work is being done is familiar, comfortable for data scientists, and reliable, and has the full complement of features. In addition, we're making available clusters of computers without any of the DevOps maintenance. You have one click to choose the cluster you want. Getting powerful computation, bigger computers, bigger than your laptop certainly, but even larger than anything you might want to be, purchasing yourself for, business or personal use, is all possible because we have managed all of that on our end. So there's not, you're not dealing with the servers going down. You're not dealing with Kubernetes being confusing. You're not dealing with AWS being inscrutable. We're handling it all for you. You never need to worry about any of that again. Then, so we take charge of the backend. We give you the one-click access to parallel computing, CPUs, GPUs, one machine, lots of machines, your choice. We will make sure that you have exactly what you need when you need it, and you don't need to worry about setting it all up on the back end, installing extra bells and whistles in order to make everything communicate. It just works. We also ensure that security, data privacy, and everything is taken care of. You will not get knocking on your door from your IT team, your security team, telling you something terrible is going on, because we will make sure that security and IT have been managed. Finally, we also have really easy integration with data storage. You don't want to have to fight with, well, the data's there and you can't get there from here. You can't move that data into this place or that place. You need data available to really make data science work. So that's one of the things that we really, really emphasize, is making sure that data storage is integrates with our tool, no matter what your data storage tool is. S3 and Snowflake, we have tons and tons of users who use those kinds of data storage options. And so we have really strong integrations with that. But that's not all that we can work with. Let us know what you're using and what you need, and we'll help you get connected to the Saturn Cloud infrastructure. So then, one question now is, this is all sounds nice, right? But the data scientists specifically have different needs than your BI or your devs. And so is this tool going to really work for the data science use case? And in fact, this is actually really what we've designed it for. Saturn Cloud is for data science, for data scientists. And so we build up tools, once again, and as I said, you can load the data from wherever you're leaving in, and you can get to work quickly. You're not dealing with the connectivity issues and, hooking this thing up to that thing up to the other thing. In addition, we make available the Dask ecosystem, which means you can use Pandas APIs and scikit-learn APIs to work with distributed data, to do parallel computing, and all the machine learning toolkit that you're familiar with and used to will just work in the Saturn Cloud ecosystem, as well as deep learning toolkits and things like that, things where you really do need that heavier computational power. That's where Saturn Cloud is really going to shine for you. And then finally, deployment is built in. We understand that deployment, getting from zero to the production use case, is really where data science makes its mark on business. And so we want to make it simple, straightforward. Deploy your model using Python once again. We have easy integration with Prefect for job scheduling. And so we try to smooth out all of the sort of spiky points that can come up when it comes to getting that last mile to production deployments. So with that, I'm really excited to be able to bring you this demo today. We're going to go right into the Saturn Cloud platform. I'm going to show you some cool features of how it works, and we're going to actually walk through how the PyTorch transfer learning workflow can be done on GPU clusters in Saturn Cloud with actually really easy minimal adjustments going from your single node workflow. So without further ado, I'm going to move us over to that. I need to switch screen shares for just a second. Pardon me. And I am really excited about this. Additionally, because this particular workflow has been a lot of fun to build. Just make sure I get the screen just right. Sorry. Okay, here we go. Great. So what you're looking at right now on my screen is the Saturn Cloud platform. So when you log in, you'll be able to see your own project space, and you'll have access to all the tools that I'm going to show off today. But a quick overview, just so you're familiar as I'm clicking around, as I'm doing some things, and when you get done with today's workshop, so you can go experiment and try it out yourself. You'll start yourself off in the project space, and then you'll have some options available to you that will sort of help you to get started. But you can also use the setup example projects button if they aren't already there. They might already be showing up for you, depending on whether you've used the product before. And this will give you starting points, easy places to begin, so that you can start from not zero and get a chance to try out what things are available and see some of the features. You can also create your own project from scratch using the button on the right. And then there are a few things inside the projects that I'll show you. So once you go into a project page, this is the project that we'll be looking at today, the one that I've already got running. You set your own Docker image. We have default Docker images available in the product, but you can also create your own. So this is all very customizable, but we don't require you to customize it. We give you what we think works well to start with. So it's the additional complexity is optional for you, but not required. And then you'll have yourself a Jupyter instance and a Dask cluster. The Dask cluster is optional. You won't necessarily need to have one of these. You won't need to create one if you're not interested in going for cluster computing resources. The Jupyter server is sort of the basic unit of work inside of a Saturn Cloud project. You also have options to create deployments, create scheduled jobs using Prefect, as I mentioned, and a bunch of other neat stuff here. We have quite a few different options and tools on the side. Documentation and guides over here can be really handy if you're starting out and you're not entirely sure what you're looking for or what you need. We also strongly recommend you get in touch with us. The Slack community is very friendly, welcoming, and lots of users on there. In addition to us, the staff are available to help you with whatever you might need. And then you can just contact us directly if you'd rather. So now if I'm in here, what I would click on is the Jupyter Lab, which I've actually already got open here. And so now we'll be able to see the project that I'm working with. This is the same project that you'll see on GitHub if you go to the link that was on the slide. It's also, I think, in the documentation for today's workshop, but you don't need to follow along or go through any of that today. I'm going to talk you through all of the steps that we're working through. This is a project that it involves a couple of different options for tasks you can do with PyTorch and Dask. And today we're using, as you are aware, the transfer learning task. So what I've gone ahead and done is opened up notebook number 1 here. So I'm going to close my file path on the side so that we can just look at notebook number 1. And so we can talk to you a little bit about how this all works and what we're going to cover in the workshop today. One of the things that I want to emphasize is that this workshop is designated for anybody who is interested in the idea of using PyTorch for computer vision in a parallelized setting. You don't need to come into this already familiar with Dask or with cluster computing or anything like that. It'll help if you have some familiarity with PyTorch, because I might breeze past a few of the basic PyTorch concepts. But we're going to talk about Dask, and we're going to talk about how all of this works and how it all communicates, so that you can go into working on your own tasks and your own projects feeling comfortable, like you know where you're starting from, and then you know the basic ideas. It's not that you're going to have every answer to every question you might have, but you'll know what you're looking for. You'll know the Google terms that you might want to find and things like that. So we're going to talk about Dask. We're going to talk about how it works, the basic kind of overview, and then we're going to talk about transfer learning on a cluster. And this is going to go for, we're going to talk about the idea of a single node transfer learning, and then we're going to talk about what it takes to put that into a cluster training and the pros and cons questions you need to be asking yourself when you're doing that. And then we'll talk about how much faster it is. As I mentioned, there's a few things to know about Saturn Cloud. We have a project, and inside the project, we'll have a Jupyter server. Clusters are optional, but those are available inside the project, and you can attach them to your server. I already have one spun up here, and we'll talk a little bit about that in a few minutes. We also have the Docker images available for you to use any type of Docker image that you're interested in, as long as you can use it. Then you can build it in Python, then we can run it for you. But the pre-built images are really great, fully featured, ready for you to start with without any pre-work involved. And so then let's go ahead and quickly I'll show you how clusters get connected. So inside this Jupyter notebook, I've got a cluster already attached to my project, but my notebook doesn't know where it is yet. And so what I'm going to do here is I'm going to run a little section of code. There's not a whole lot. And what it does is it uses the Saturn cluster function to identify there's a Saturn cluster. I'm going to go look for it. I'm going to attach it to this object. And then the Dask client knows this is the cluster I'm looking for. So now we've got our client object. It is a defined item, and it has workers already assigned, and everything is all set to go. Now I'm going to check to make sure that these machines are GPU enabled, because the work that we're doing today is going to involve using GPUs. And so we're good. So this is testing whether GPU is available on the machine that I'm using right now. We can also do that to check that GPU is available on all the workers. And notice that we're using client.run, run being a method on the client object that we can use to run little utility functions, as it were, on all the workers. And we'll talk more about that when I talk about Dask in the next notebook. So another thing to keep in mind is that we're going to be needing to get access to data. And so one of the nice things, as I mentioned earlier, about Saturn Cloud is that we have easy interfaces to get access to lots of different data sources. I'm using a public data set here that's on S3. However, if you chose to use an S3 bucket that was not public, all you need to do is add credentials in the PyTorch or in the Saturn Cloud environment. And you can see here under Tools, Credentials, add your credentials right there, and then you would be ready to go. So I'm going to go ahead and run this and make sure that our files are where they belong and that we'll be able to access them when we need to. But if you wanted to access a private S3 repository or S3 bucket and use that data, it would be no problem. It would work almost exactly the same way. Looks like we've got pictures of docs where we expect them to be, so we are ready to move along. So I'm going to go ahead and close this notebook. I don't need to save it. And then I'm going to go ahead and open up number 2 here, which is the Dask basics. And let's talk about Dask. Let's talk about what it is that we're actually dealing with here. Because I've talked to quite a bit at this point about how we're using everything is Python here. It's really not going to require you to start learning new programming languages or get into real complex, machine code or anything like that. Dask is a framework that enables you to parallelize Python code. It's Python, but it's targeted at the idea that you might need to accelerate the performance of your Python, and it uses a new framework to allow you to do that while it's still Python. You can use Dask with pandas or NumPy, scikit-learn. It works on a single machine. If you want to create a little cluster on your own machine, that would be called a local cluster. You can use it on multi-machine clusters like we're going to do today. And we have there's some great documentation about how Dask works and all of the stuff under the hood. But what I want to show you today is sort of the user endpoint, how it works, what it looks like, and what concepts you need to understand in order to be able to use it effectively right out of the box. So when we talk about parallelizing, what do we really mean? We need either to add more memory to our available sort of resources. Say we've got a data set that's too big, pandas can't hold it, laptop can't hold it all at once. You might want to chunk up that data and distribute it over your cluster. That means the data will be stored in a distributed way, but you access it as though it was a single object. We'll show an example of that in a minute. The other option is that your data is not so big that you can't handle it, say, but that your computation takes forever. You might be doing a really complex computation, you're training a really big model, hyperparameter tuning can end up like this. And those are situations where you don't necessarily need to distribute your data across the cluster. You need to distribute your computations across a cluster. You need more computers doing work for you at the same time so that you can get this done before you're old and gray. So those are the choices of sort of use cases for parallelization. Those obviously intersect a lot. We have use cases that come up that are similar that use both of these situations from time to time. So Dask is good for both of these. And so the first thing I want to talk about a little bit is the idea of delaying tasks. So when you take a Dask framework to use that to take computations that you want to distribute across a cluster, what you want to do is to say, create a task that isn't going to run itself immediately. You want to take a task, say, okay, you're ready to go. We're going to set you aside, and then we're going to create more tasks that are all set aside. And then we're going to en masse send you out to the workers to do the computation. And this is kind of the idea of what's called lazy evaluation. Create a function, and it's going to hold on, and it's going to sit and wait until it's told explicitly to actually compute. So other kinds of functions will be computed instantly upon call. Eager functions is their eager evaluation. But when we use lazy evaluation, that means we can rearrange who's going to do which work and when, and Dask will actually handle that for you. It's called task graphs. So for things that are built natively in Dask will be lazy automatically. They will be delayed computation without you having to instruct it. Sometimes, though, you've written something custom in Pandas or Scikit-learn or Base Python or NumPy. You've got a whole thing that you've written a big, complicated function, and you might want to run it on multiple, workers in a cluster at the same time. You might want to run it as well as running other things in parallel with it. And you don't want to rewrite this whole thing again. As we mentioned in the very beginning, rewriting all of your code is like the bane of a data scientist's life, and it's a waste of time. So what we can do is use what's called a delay decorator. And so I'll show you an example of actually how that works here. You'll create your function, the function you would have already written. You'll decorate it with dask.delayed. And then later, when you're ready to run it, you'll either use compute or persist. And I'll explain what those are in a minute. So here, let's take an example. If I look at this function, it's just a, x to the power of y, nothing complicated about it. Run it, and we get our result. This is an eager evaluating function, nothing fancy about it. So let's say I take Dask and I add this one line at dask.delayed, and I run it again. We do not get the same result. You'll see I'm getting a delayed object here, and it's just a delayed object that contains all of these tasks that I've asked it to do, really just the one, x to the power of y. But it's waiting. It's waiting for me to say, okay, now go. It's got all of the arguments it needs. It's got all of the external information it needs. It just is waiting for the instruction. So now if I run .compute, we get the same result. And that's really the concept underlying delayed. It's you get it ready, get it set up at the starting line, but you don't, say go until you're ready for it. So we can chain these together. And that's kind of a neat thing too. And that really is what creates the powerful option to create task graphs, to have multiple tasks that rely upon each other and have interdependencies, still be delayed and still be parallelized. So if I take X, same, we just ran, but then I create Y that has X as an argument. And then I take Z, which has X and Y as arguments. And now I get one delayed object that is Z. Okay? So let's see what that looks like. Looks like this. I've got lazy exponent called once, lazy exponent called twice, and then multiply called once. These are all lazy. They're all waiting because the lazy exponent function is the starting point, and it's delayed, so everything is going to be delayed waiting for it to go. So now I can take Z, compute, and we get a big long number because, of course, these are large figures that we're dealing with. And that's the kind of power that is available because Dask has these lazy evaluation concepts built in. You can start creating graphs like that and set up your entire computation path, but not have it start and not have it running until you're ready for it to go. So persistent compute are important concepts, and this is something that really I struggled with when I was first getting familiar with Dask. There's the idea that you might have work running on your Jupyter instance right here, right in front of you, and then you might have stuff working on a cluster of worker machines. If you use compute, you're asking for all of the computations to be that are queued up to be run, finished, completed, and then you want your object to no longer be distributed. If you were starting with a distributed data object, say a Dask data frame, it's not gonna be distributed out there in the workers anymore. It's gonna go right here. If you have a large data set that's too big to be housed on your single Jupyter instance machine, this could be bad. This could be catastrophic. But if it's small enough data, you can get it right to the local machine that you're on, and everything can be fine. If you want that last step to be skipped, you want to hold off and not take all of the data that's distributed across your cluster and bring it to the local machine, then you use persist. And I'll show an example of the difference between those right now. So if we use the Dask library, we have a Dask data frame, and we can just pull up a data frame that is part of the default stuff that comes with Dask. And it has 30 partitions. So it is broken up into 30 chunks across our cluster. We don't have 30 workers in our cluster, but it's got 30 divides in this data. So that's just an interesting thing that you can find out about any data set that you're using that's distributed. So we have 30 partitions. And so now let's run some computations on this data frame. Let's mess around with it, let's group it and do some filters and this and that. So what we've gotten it down to is actually a single series. So now it's a Dask series, and it doesn't have any partitions anymore. Now it's one thing. But we could repartition it. We could break it up again into 3. So we can make it now a series that is grouped into 3 partitions. The partition shape and size on the object is up to you as the user, but Dask will have opinions, and it will default if depending on the use case and depending on the computations you request. So now we have persist or compute. What if we take a look at this end partition, this df4 object that we've created? Now we've done filters and messes around and stuff like that. It's a Dask series, but let's look at it. So it's 3 partitions, it's a float, and it's got Dask name repartition 161 tasks. Why is it doing that? It's because we haven't computed anything. We've been messing around here. I created this object. I did all of these things. I didn't do anything actually, because this data is lazy evaluating. So it's queued up 161 little instructions that I've given it, and it's ready for like, okay, is it time to go now? So if I'm going to say persist, it's going to take a sec. But now I've got all of the same stuff except this. This line tells me that all except 3 tasks have been run. What's those 3 tasks? The parallel distributed state of the last object, because it's 3 partitions. 1, 2, 3. The last thing they can do is be brought back into a single object locally. So now I can do compute, and we can actually look at it. And so as you'll see here, this isn't a Dask object. This is a pandas series now, and it's just a little series of floats. That's what you get back when you finally run compute on the object at the end. No longer a Dask object. Now it's pandas. You can do anything you would do with pandas. So one more task, one more thing we need to figure out. So we're here, we're working on our Jupyter instance, and everything is going great. What do we do if we want to actually tell the workers to do something? We've got a cluster, there's workers out there, there are compute resources sitting there waiting for us to be used. How do we tell them we want to do something that's on the actual worker computation? We've dealt with the distributed data objects a little bit. So let's take a look at our cluster. Similar, we've already figured this out. We know how this works. There are different kinds of workers. This is interesting. Helpful tidbit, just in case you had ever wanted to know. These are the kinds of machines that are available currently through Saturn Cloud. This is the sizes. You can go from teeny tiny to huge GPU resources. It's kind of nice. And so we have our client object. That is our connection to the cluster. This is the way that we send communications back and forth. And we have a few ways that we can do that communicating. We can use submit, or we can use map. Submit is take this task, run it on a worker. Any worker, whoever's free, doesn't matter. You decide. Map is take this list of workers, take this list of inputs, and one function. We're familiar with map in the kind of general Python way. And then distribute, take the task, run it on object 1, object 2, object 3, and then distribute those to the workers. Once again, though, it's going to distribute them to the workers that are free in the way that they're available, most efficient way that it can find. We used run earlier, as you remember. That uses one task to every worker simultaneously. That can get really resource intensive and overwhelm the workers fast. So you want to use that just for the small utility tasks, really. Let Dask choose as much as is reasonable how to distribute work to the workers, and it will actually be more efficient. Dask is designed to be able to figure this out. If you need to designate exactly like one task per worker, which is in fact what we're going to do a little later, you can specify the number of the worker that each task should go to in submit. So you say submit and you give it the task, and then you say worker number 0 or 1 or whatever. So that's an option too. So I'm going to show you a little example of how map works, just because this is kind of fun. We can actually just run it straight away here. So I've got this list of lists, and I've got my lazy exponent function, right? So we've got these numbers that are all going to be computed. And so I'm going to go ahead and run this. And it was just a second. But we have to make sure, now that we've distributed work out to the workers, they're waiting. It's lazy. They haven't been told to compute anything yet. We need to make sure that there's an instruction there that says, okay, now we got to get the results back. Because otherwise they're going to be on the workers, and those results are not very useful to us if we can't get them back to our Jupyter client to see them. So then we'll run .gather on this object we just created. So we do that, and now we have our gathered object, and now we can say compute. So we've got compute on the object that we've just created, and that should just take a moment. So now we can actually look at the results finally. So we've got three lists in our overall list. So they're all finished. Good news there. And we got numbers. We can look at them all. 181, 15625. Those are the results from these right here. So it all ran in parallel for us, not one waiting for the other. And it's actually really easy to do, even with these small examples. This is in the GitHub repo, so if you come across confusion later about, okay, what was gather, what was compute again, please feel free to reference this. I find it very useful to help sort of explain the basics so that then we can get into the crazy complicated stuff. So with that, we are now ready to move right on to our PyTorch use case. You've got the familiarity with Dask that you're going to need in order to move forward. So go in here. And so I'm going to go into the transfer learning demo folder, and we're going to start with notebook number 5 in here. So the transfer learning task, I'm going to explain a little bit. We're talking about we're using the Stanford dogs dataset, which is images of dogs designated by breed. And in our task, we're going to start with the ResNet 50 pre-trained model, which is trained on the ImageNet dataset, which the Stanford dogs dataset is a part of. So the ResNet 50 pre-trained, it knows the breeds of dog. It also knows tables and chairs. It knows, fish, and it knows reptiles. It knows all kinds of things. We want to use transfer learning to say, okay, ResNet 50, we're going to start with you, but we're going to really, really target you so that you are best at dog breed identification. We're going to target its training a little bit. And this is a nice way to approach using deep learning for a classification like this, because a lot of models already exist that have some knowledge that we might want to use as sort of the foundation for the work that we're going to do next. So we're going to pre-process the data and make sure that we have all the infrastructure ready to parallelize, and then we're going to actually run it. We'll look at some results and see how it performed. So once again, we're going to start our cluster. Remember, the notebook needs to know where the cluster is and what it's looking for. We've got our 3 workers. We've got 96 cores. Good stuff. Just always check and make sure that we have the GPU assigned as a device, because one of the things we need to do is make sure that we instruct different tasks, different objects, that we want as much computation as possible to be using the GPU to do it. So we're using the Dask PyTorch DDP library, which is something that was developed here at Saturn Cloud, to handle some of the work involved in taking PyTorch training tasks and making them parallelized using what's called the Dask, the distributed data parallel tool framework, I guess. And so one of the things that we've built into that is a data loader object that goes direct, a data image folder object that loads direct from S3 because we found that we were using S3 a lot to house the data, and we didn't want to download it to disk and then use it in our model. This way, we can make sure that the workers can individually load direct from S3 on a just as needed basis, sort of a just in time data loading. So I'm going to go ahead and load up some of that, make sure that that's ready. And then the pre-processing is really simple. This transformation pipeline is all we're going to do. We're going to crop, we're going to resize a little bit. We're going to make sure that we've converted to the tensor object. And then we can just use this S3 image folder class that I mentioned and pull it together. And we use the anon equals true argument just to make sure that our instance knows it's not supposed to be looking for any credentials because this is a public repo. And so that's an important tidbit to keep in mind. So there we go. We've got the function. We haven't run anything yet. In the case that I'm going to be using here, and this is entirely optional, this may not be relevant for future use cases for you at all. I've got the Stanford dogs data set and the ResNet 50 label data. They don't actually match index to index. And I'll show you how that looks right here. Because it's kind of a case where if you're starting from a transfer learning model, you need to correspond to the labels that that model was originally trained on, if it's classification like this. So you might find that, for example, your data set, in this case, our data set, starts with Chihuahua, and that's, the first 5. But if we look at the ImageNet data set, it starts with, fish. And that's going to be a problem because our model thinks number 1 is goldfish, but our data set thinks number 1 is Japanese spaniel. So we've got to fix that. It takes just a second, and I've just written a little regex function to do it. Like I said, this is optional. This is just an interesting tidbit that if you want to do this whole example, soup to nuts yourself, just keep in mind. So I'll go ahead and make sure that our classes are right. Okay, now Chihuahua is 151, which it should be. All good. And we make sure that we haven't missed any. Everything is exactly the same length. Perfect. Okay. So the next thing we need to think about is, because this is a classification model, we want to make sure we're creating a training flow that's going to give us evaluation samples to look at. We're going to make sure that it's going to work with, by the best standards of, highly, unbiased machine learning. So I've created a function here that will do train, test, split, and produce 2 data loader objects, one for a training sample and one for an evaluation sample. You don't need to know a whole lot about the inner workings of this other than that that's what this is for. But I also want to mention that we're using multiprocessing, which is important because the fastest thing that is the slowest part of the task that we may be running is actually loading the images up. So we want to make sure that we're using a multiprocessing context for the data loaders. It's going to give us snappy service when it comes to loading images parallel, so that the GPUs on our workers that are doing the classification task are not held up by loading the images themselves. So this is pretty much all of the pre-processing that we require. This is really the only stuff that you need to do. Make sure that your image data set, in this case, image data set, is labeled correctly. It's going to match up to your data that your model is used to. And then make sure that you've got your train, test, split sampling ready to go. Make sure it's going to be shuffled. I've actually just set up a manual shuffling process here, but make sure it's going to shuffle so that the different workers get different information. So let's move on to notebook 6A. So you have the option here of 2 different approaches to this. I'm going to use 6A, and the difference between these is very simple. On 6A, I'm assuming you have an S3 bucket where you can store model performance statistics, so we can save them out and then use tensorboard to review them. If you don't have an S3 bucket, it's totally fine. We built a results handling toolkit into the Dask PyTorch DDP library that lets you train on a cluster, but save JSON results to the client setting. 6B shows you exactly the same tasks, exactly the same work, but it will show you how to save those results to your local setting. And instead of using tensorboard, you can use notebook number 7, which has some plotting and some small functions that allow you to retrieve those results and look at them. I think that tensorboard is really cool. We are really excited about making it available to our users to integrate directly with Saturn Cloud. So I'm going to show you how that one works today. But I just want to make it very clear that this is not necessary for you to take advantage of the whole Saturn Cloud ecosystem and to use this toolkit for your deep learning needs. So let's go ahead and close the folder up so we have our full screen. So I have, we ran a whole bunch of stuff in notebook number 5, pre-processing our data and that stuff. I've already saved all of that to the side in a script called setup2. It's in the repo. You should be able to get to it. And so I'm going to go ahead and just run that so that it makes sure a cluster is up, make sure everything is ready, make sure we have the functions that we need to have. So there's no point in rehashing the whole thing. So we just got that ready. So now I've got a few things that I'm going to import, and I'm not going to talk about these so much right here. I'm going to explain these as we use them, but just for your reference, this is where you'll find the imports from the PyTorch library that you're going to be using in order to make this distributed training possible. So if you're going back and trying to cobble this together for your own use later on, this is where you find those. And so make sure that we're all up and ready to go. Looking good. So we're going to use a very sort of standard training flow for our PyTorch model here. So we're using cross entropy loss for our loss function, SGD for optimizer, nothing real exciting. We've got the training and evaluation stages, as I mentioned, and we're going to use this training set using batches of 100. So the training workflow should look really familiar to PyTorch users, adding like 3 lines of code, honestly, to make this go from a single node training to a parallel thing. And I'll point out those elements as we go. And so let's talk about some of those now. I'm creating a summary writer object for tensorboard to write things out. Nothing fancy about that, but just so you'll know it when you see it, and so that you're not confused about what that's for. That's what this is. We're going to make sure that our model is aware of the need to use GPU resources, and this is going to show up later on. As I mentioned just briefly earlier, we've got to make sure that our model object, our data, and whatever we're working with understands that there's GPU compute resources available, and it should be using those when possible. And so we call this .to device argument on the objects themselves that's built in. This is a PyTorch feature that will make sure that they know GPU is available. That's what you should be using. And then we have the DDP wrapper. Now, the Dask distributed data parallel framework for Torch allows you to create a model object that understands that it has multiple threads of work being done that are all intertwined with the same object. I'm not going to go into a ton of deep detail about how DDP works today, but we have a blog post that is linked here. You can also find this on our website that really goes into detail about how DDP works. But the general idea is that you start with a master node, say worker number 0, and it is going to sort of be the holder of the state of the model. It will pass the model's sort of current weights and biases out to the workers, and the other workers and worker 0 will all train as usual for an epoch. They'll go through their iterations, the same batches will be run through, and everything will go as according to plan. The end of the epoch, they all communicate back to worker 0 again, and they say, this is what I learned during this epoch. Worker 0 aggregates that, creates the current state of the model after that epoch, distributes out that state again to all the workers, and then they start the next epoch all from the same place. So they all kind of diverge a little bit during the epoch, learn different things, summarize all of the learning from all of the different workers at the end of the epoch, and then we start again. So that's the general gist of how DDP works. So now I've got a couple of, like one utility function that I've created just to make sure that the training is always identical between, or the process is always identical between training and evaluation. This is just a thing I like to do, but you can just place this code directly in the actual training function, and it'll work just fine. But when you see iterate model, this is just the training part. And so now we've got our transfer learning function. Normally, you'd probably just run this all in just a plain chunk. You wouldn't wrap this in a function for a single node training because you really wouldn't need to. But for our use case, remember what we talked about when it comes to take your function, make it delayed, and then distribute it to all your workers, and they will all run it. That's exactly what we're going to do here. We're taking all of the work we want them to do, we're creating a function, and then we're going to distribute it to the workers, and they're all going to run it simultaneously. And that's how they're going to understand that they're supposed to be training in parallel. They'll be training the DDP model simultaneously and communicate. That's why we need to wrap our whole training thing in a function. Anything that needs to be involved in the training process needs to be contained inside this function, the run transfer learning function. As I mentioned already, we've got our summary summary writer, which is the tensorboard object. We've got a few other small things. We're making sure that our device is the GPU as CUDA device. And we've loaded our model. This is actually something that comes from the PyTorch ecosystem. They have a library that is designed to just provide sample data sets and models and things like that. And so that's where we're getting our ResNet 50 from. And we're calling pre-trained true so that we get it already trained on ImageNet. You could just get the layer architecture and not have it trained on ImageNet at all. And that would also work if you run it the same way. You'll still get results and you'll still be able to train the CNN the way you want. And so then we're wrapping our model in DDP so that now PyTorch knows this is a parallel model, training in parallel across multiple machines. All of this other stuff is just the same stuff you would use in any other PyTorch workflow. This is not different for being distributed in any way. This other stuff, now the model knows that it's distributed, everything else can be the same. I've added some, stuff where I'm tracking results and monitoring the statistics as it performs, but none of this stuff is any different for being distributed at all. So let's go on down. I'm using the writer object that we created for the for tensorboard to write my results out, and we'll see the actual examples of that in a minute. And then we got our evaluation section does exactly the same thing. We already wrapped our model in DDP above. You don't have to do it more than once. You can just do it the one time. And that's it. And I'm saving checkpoints of the model object every so often in order to make sure that we can check the model's performance, or if we get to a point where we want to look back at a particular state of the model, we can. So if I run everything up to this point, I can actually show you what it looks like when it starts to run, which is kind of convenient. So at this stage, I want to pull out the ImageNet classes because that's the target that the model is trying to achieve. So I want to make sure that I have the classes, that pulling the model directly from the PyTorch library doesn't give you the classes. So that's one thing I need to do. And client.restart here is a useful utility function that will clear all the memory on your cluster. Because remember, we've been messing around and we've been doing other stuff with some of these other notebooks. It's just convenient to make sure that the cluster is completely clean when you get started training a new model like this. It doesn't change anything about the memory in your Jupyter instance. It'll just clean up your cluster. So then I've set up 6 epochs. Batch size is 100. I've changed 80-20 split for training and evaluation. And I've got a learning rate set. And then if you want to, you can split your data across the workers. So each of our 3 workers is going to get 33% of the data. That's what I'm doing here. You can choose to do that subsetting whichever way makes sense for the task you're working on. You might find that you want all the workers to see all the images. You might not have enough data to do that kind of a split. It's very flexible depending on the needs of your use case, your training set, and the question you're trying to solve. So I'm going to run that. So now I've got my dict of all of my start parameters. And so here's when I'm going to actually run it. Dispatch.run is a tool inside the Dask PyTorch DDP library that just wraps up client.submit, but it ensures that we are sending one task to a worker and only one task to a worker. You don't need to know the underlying guts of this, but if you're interested, we have it all on GitHub. It's an open source library. You're totally welcome to read the code and ask questions. But the thing that you need to know about this is that we want one worker per task, so that each one is training the same model, starting from the same point, but on different data, and then they can do that backwards communication thing that I talked about. And so we go ahead and run it, and it's actually running already. You'll see that these are called pending, and you can just take this futures object that we've just created and run it again, and it'll just keep telling you it's pending and say, hang tight, don't worry. What we can do now is we can look at our dashboards. I'll pull this up, and we can see the work being done as we go. Get these side by side. So we've got our workers, and they're still thinking. They're not moving too far yet. It's going to take a second for it to really ramp up. And then we'll start to see that the GPU utilization will ramp up as well once that work has begun. I'm going to let this go ahead and get running right now. We're not going to worry about it just yet. But I am going to show you the actual results as they look in TensorBoard. And once I get done with this, then we'll be able to move on to our Q&A section, and then we can talk a little bit about how this all works, and maybe I can answer some questions about your use cases. So I've run 6 epochs using this exact workflow. I ran it just earlier today. And this is the training path that we saw. I've got training and evaluation on the epoch level showing right now. So we started out, because it was a pre-trained model, the average accuracy per epoch was between 88 and 94, 95 correct, depending on evaluation or training mode. And that's out of 100. So it's pretty good. It starts out in a pretty good place. It's already been trained on these images in addition, on these labels in addition to other things. But as you can see, as the epochs move, we get much higher. So now at the end, we're between 98 and 99 out of 100 accurate for the model for the accuracy. And then the loss values, you can see here, we get a nice smooth decline of loss values as well. But let's take a look, because it's interesting to see, like, what did the model actually think? So we can look, because tensorboard is pretty neat. We can look at the images themselves. We can see some examples. Maybe I need to refresh. Oh no, I'm sorry. My tensorboard must have shut itself down. Let me quickly see if I can figure out what is complaining about. There we go. Forgive me, that seems to have been upset. But the point being is that you can use tensorboard to view your results without having to save the results to local memory, which can be, intensive. And saving them to S3 is really convenient, because then you make them available to your colleagues and whoever might be working on the project with you. And we've got it. And you can also make sure that those results are available to others. So here now we're looking at our job, and you can see the GPU utilization is firing very high. And you can see that the CPU also pipes up when the GPU is running. And that's because when we're loading the images and doing the image transformations, that's going to run on GPU or CPU, pardon me, while the image classification and the actual machine learning is running on the GPU. So when they're both running, they're both at high utilization. And that's kind of convenient. I'm confused as to why that's not turning out the way I wanted it. Sorry. Okay, so with that kind of covers the basics of what I wanted to show you. I want to give you one more review of a few things. I see we've already got some great questions coming in. So I'm going to take one last note that I want to talk about, which is that we have future events coming up. And that's really, really exciting. We have a great event coming up soon with NVIDIA and DoorDash, where Aaron, my colleague we met earlier, is going to be talking about GPUs in the cloud and working on data at internet scale, meaning scale of like large commercial, like custom internet companies, which have to scale up data to just extreme levels in order to be able to serve the needs of customers. And I think that's going to be a really exciting event. So I hope that you'll join us for it, because I'm really looking forward to it. We have office hours, which once a week. We have data scientists, our CTO, other folks around the team made available for you to ask your burning questions about Python, about PyTorch, about Dask, about whatever you're interested in. We would love to talk to you. So please feel free to visit the link and join us. And then, of course, join us on Slack. Drop us an email. I am Data Stephanie on Twitter. We have at Saturn_cloud. And we would love to hear more from you.